Okay, let's get in chapter 9. Chapter 9 is fun. Bonding.
Is this the one where it's like two rods or it could be one?
Yep. Well, this is your chance to really have a good time with them. Because, yeah. I'm sure probably before it was, I don't know. It's going to be fun this time, though. All right, yeah, so we're going to talk about chemical bonding. Take a little break from the math for a couple chapters before jumping back into it. So just a little bit of a roadmap for the rest of the semester. Chapter 9 is chemical bonding, Lewis structures. Chapter 10, we're going to talk about the theories of bonding, so what we call valence bond theory and molecular orbital theory. So sort of the why or what's happening energetically for these bondings and the consequences of that, which are things like shapes and some other stuff like that. Then we will get into intermolecular forces in chapter 11. And then we will get a little bit probably into chapter 12 and probably won't make it to 13. But that's a lot, and we only have 2 weeks basically, and then the final exam week, so 2.5 weeks. On the next exam will be more conceptual. Yeah. The third exam will be like the stuff we've just been talking about, the trends, Lewis structures, drawing things.
That gives me 3 weeks to forget.
The next exam is July 3rd, the day before we have a day off. We do on Wednesday. Yeah. Quiz on Wednesday. Over the chapter 8, yeah. So we did the 7th, so chapter 8.
So we're getting through chapter 13?
No. We will probably get into chapter 12, but not complete chapter 12. We just stop here.
I think we're good.
Yeah, I think we're good. Sure.
8 chapters in 8 weeks sounds like plenty.
Are we taking that ACS exam at the end of this?
Yes.
I'm still doing better. Normally I'm like at 85 just generally.
Yep. Did anybody order that study guide from the ACS?
What do you think?
I don't know. I think if you're planning on going on and taking another semester of general chemistry, then it's worth it because you'll use the same thing again for the second semester. If you're only taking this, then maybe somebody will be nice and just like scan you those pages that apply to this exam or something. So $20. All right, let's look at the different modes of bonding. So you know the 2 types of bonds, right? We've mentioned them. Ionic and covalent, yes. Also known as covalent if you're eating a sandwich. It's okay. So those are intermolecular forces. Those are not technically bonds, even though it has the word bond in them, which is confusing. But we'll get into that in chapter 11. But there are some other types of bonding, but they can fit into those categories of ionic and covalent also. All right. So we talked about ionic solids. We talked about covalent solids. Let's look specifically at representing covalent compounds, and then we'll look at representing ionic compounds, lattice energy, and go on from there. So one way that you'll see this represented is something called Lewis dot structures. Yeah. And we're going to start from the very simple, get to the sort of complex, but then if you go on to organic chemistry, this is going to become really, really important because that's basically all that you do all the time. So it's a really important basis for doing a lot of that kind of stuff and communicating chemistry. For right now, for specifically these dot structures, all we're really interested in doing is expressing the valence electrons on the symbol of the atom. So if we take oxygen, for example, we know the electron configuration for oxygen is helium 2s2 2p4. And for the sake of bonding, at this point in this chapter, and we'll see why that works later, we're not going to separate into the s and the p's. We're just going to say oxygen has 6 valence electrons, which we can also get from its column 6a. So to express that, we can draw O for oxygen, and we can just draw 6 dots around the oxygen to show the 6 valence electrons. Now, one way that that's often done is to put them in 4 pairs around the atom. And the reason for that is we know that there's a special stability to 8 electrons because that's a full valence shell. And so it gives us a really clear visual clue as to how many electrons it has, how many electrons it needs. And so we leave those last 2 electrons unpaired. And then if we know that a full shell would be 2, 2, 2, and 2, it's really clear that this is 2, 2, and it's missing 1 and missing 1. This is also going to be important for when we talk about bonding. So that's all that Lewis dot structures are. We draw the atom with its electrons in dots around it, and it gives us a really clear picture of how many valence electrons it has and how many it needs to get up to 8, that octet rule.
Does it matter which side they're on? Like if you
No.
put 2 on the right?
No, it doesn't. No. And if you haven't heard of this, the octet rule it's not a very strict rule, but it's basically just saying usually atoms are more stable with 8 valence electrons. There's lots of exceptions to this, like the smaller atoms, hydrogen and helium, only have 2. We'll see lots of ones that can have more. That's why it's not a real strict rule, but it's a usual rule. Nikki, do you have a question?
Yeah. What would have happened? I think you said it, but I missed it. If you didn't put those 2 electrons separately and you just put them so you had one empty side of the oxygen.
I mean, it wouldn't bother me, but I think the purpose of drawing the Lewis dot structure in this way is to have those 4 sides, the 4 pairs. And so if you had only 4 electrons, like with carbon, you'd draw 1, 1, 1, and 1.
Oh.
Shit like that. Okay, does that make sense?
Mm-hmm. That was my question.
Okay. Yeah, it just says a maximum of 2 per side. I mean, if you put 2, 2, and 2 for oxygen and left one blank, I wouldn't mark that wrong. If you're doing your homework, they might, because it might be a stricter rule than that. But I think the point is just to express how many valence electrons are in there. Okay. So one way we can use Lewis dot structures is probably the simplest way is to think about ionic compounds. So if we look at something like potassium, we would draw its Lewis structure like this. And if we looked at chlorine, we might draw its Lewis structure like that. All right.
Your attention, please. An emergency is in progress. We must walk to the nearest exit and leave the building.
Is it still raining?
Do not use the elevator.
So if it is raining, if you don't want to go outside, you can go into the L building, like by the bookstore, because those are fire doors. But we should go out this way. I'll lock the doors. Let's head out.
Your attention, please. An emergency is in progress. You must walk to the nearest exit and leave the building. Go to your assigned area. Do not use the elevator. Walk to the nearest exit. Do not use the elevator. Walk to the nearest exit and leave the building.
he wasn't confident enough to teach us harder skills, so we were really bad with that.
Mine was not in the way when he was spotting me. Like he'd run in as I was running, and then like hit me.
Professor Walker, that woman is so nice.
Yes.
What's her name again?
Julie Ellison.
So,
Oh, I think I actually remember.
so I was doing Sukes, so round off back off the ball. And I was doing it on the mask, and he's like, well, I don't think you're ready, I don't think you're ready.
Why are you guys all in here?
They just
We've
opened
been
the door.
there the whole time.
We just got
It was all fun. So,
You guys all look so comfortable. I'm like,
so I pulled my suit and landed on my back with magic. So I was getting a lot of air.
Yeah.
So he's like, okay, you're ready, you're ready. So I go into my first one. I probably could have pulled a double and landed really close.
Okay.
Like, I got a like that's, I couldn't twist, but I could get power.
Yeah.
So my coach,
I don't.
who hadn't
We couldn't
taught
figure it
us
out. They said it was on the third floor, like
8 or
chemistry,
10 years,
but nobody was doing lab, so it might have just been like a malfunction of something that,
and I go,
yeah.
wham, like landed right here, just with an exhortation because he didn't know how to stop. And then I got
maybe
he's
like,
oh my God, sit down here.
just the collective
I'm fine.
anxiety about the
Let me
exam
do
in
it
class,
again.
like
Let me do it
shot
again.
fireballs downstairs somewhere, just ignited something psychically.
There were 3 left on the floor.
Fire
So
doesn't
left
sound
back,
like a
the
typical
whole
fire.
school, whatever.
Like the
No.
And you know,
I thought it was like gonna be like a tornado or like an active shooter or something. I got so scared.
Oh, it definitely startled me, yeah. I've heard it a bunch of times, it was still scary.
Anyway, so the sisters
that's so funny.
competing, the other
People
sisters
just
still have
walked
to go.
into like
The one that's
same
competing.
building except just like their doors.
But they're that's the point of fire doors, is fire doesn't go through them.
It's
And
funny to me. I
oh
don't
my
know
God,
why.
they got about 1 1/4.
Like, what if it
hit the
hits
ground?
the wall? Like a wall? I don't know.
Smacked her.
So,
tibia,
I mean, the way those
hit
systems
her
are supposed to function, if it was turned into some
And
massive
so
thing
the
that was
room
not
silence,
contained,
the other
then the
group
fire
was
alarms
silent.
would start going off in that building too, and then you would get out of that building. So that would be the idea. But, I mean, the way a building like this is built, even if a fire started in this room, which is not a lab or anything, but a fire could be raging this entire room, and this room would contain that fire. It would not spread beyond that room,
Do you
this
ever
room.
see someone get grip lock?
So,
Do you know
I
what
mean,
grip lock is?
it's possible if a fire got really out of control that it could start to spread, but there's just not enough fuel. Like, buildings are designed for that. There's sprinklers in all the rooms, you know.
Me too. So there's 2 different filters. So we-
All right. Should we continue?
Sure.
We're all good?
Yeah, she did.
Do you want to do like a gymnastics demonstration before we start? Do a flip or something?
Chris, do it.
No? Okay. No, he's tired. He's tired.
I will by the end of the semester if you really want.
Chris, do
I-
a cartwheel.
If you get
No, I don't want somebody to get
I'm
hurt.
standing back, you gotta give me like. I'm not saying that.
There you go. All set. All right. So when we left,
Hey, if I do that, I'll do it right now.
that is not one of the course objectives, so I don't think that works. But also, still not one of the course objectives. All right, so when we left off, with all the excitement, we were just about, I'm sorry for the suspense, we were just about to talk about what happens in this situation, where we can have ionic bonding as a result of a transfer of electrons. So we see clearly with the Lewis dot structure Lewis dot structures here, potassium with 1 electron and chlorine with 7. And we can also see that potassium is likely to give up that electron, chlorine is likely to accept that electron. You've probably seen this kind of thing before. So we can end up with 2 ions, potassium and chloride, which in the book they forgot the L, and so it says carbon, but it actually should be chloride. But luckily they re-release this every couple of years, and this is the 4th edition, so hopefully in another 3 editions they'll catch it. All right, so we've seen things like that before. Now, when we talk about an ionic bond, we don't draw a line between these. We don't show them like connecting in a specific way, because we really save that for our covalent compounds that we'll talk about in a minute. But one thing we can talk about is something called lattice energy. We saw this a little bit in the solubility when we were talking about solubility. And we talked about how there's kind of a competition going on when you try to put something in solution. The water molecules surround the ions, and that releases energy. That's exothermic. But you also have to break apart all these ionic interactions in the solid, and that's endothermic. And you kind of have to balance those to decide whether that's going to happen or not. And a big part of that energy of breaking apart the solid is called the lattice energy. So technically, the lattice energy is defined in the opposite direction. So if you imagine this reaction happening, if you imagine a free sodium ion in the gas state combining with a free chloride ion in the gas state to make a sodium chloride solid, so free ions combining and make a solid, we can talk about the overall standard change in enthalpy, which is another way of talking about the energy. And that is called the lattice energy. So the energy that comes out from that reaction is called the lattice energy. Now, thinking about that process just like if it were actually happening, would you expect that to be an exothermic or an endothermic process? Would you expect it to release energy, or you'd have to put a lot of energy in to have ions in the gas state become the solid sodium chloride? In? Out. In? Out.
Well, to become a solid, wouldn't it be tend to go in, because then it wouldn't out be the reverse?
So we want to think about what do you think is more stable? Is it more stable to have free ions in the gas state, or is it more stable to have a solid compound? Solid compound. So more stable is another way of saying lower energy, right? More stable means lower energy, lower potential. Less stable is higher energy. So what we're really saying is we're going from a high energy situation to a low energy situation. So is the delta H going to be negative or positive? Negative, right. We're going from up here to down here. So the net change is negative. All that energy is being released.
Quick question. So is chlorine gas just Cl, not Cl2?
No, chlorine gas is Cl2. This is chloride ions in the gas state, which is a super high energy, like unusual thing. This is not elemental chlorine gas. Right. So as you can imagine, that number is pretty high because the idea of having free ions separated from each other is much higher energy than having them together in ionic bonds. That's the whole point of bonding. But this is how you measure how strong that is. So if you're interested in it, you can look in the book for something called the Born-Haber Cycle, which describes all the energies of the different processes that has to happen. So like sodium has to become sodium gas, solid has to go to gas, then chlorine gas becomes chloride, and then they have to be ionized, and then they come together. All this stuff goes on when you're actually making a compound. We're not going to go through all that right now. What we are interested in is just some general ideas about how the lattice energy is affected by the constituents of it. So if you look at a compound like sodium chloride, how does its lattice energy compare to other compounds? So what are some effects that you think might influence the size of the lattice energy? Like how strongly an ionic compound can bond together, basically. What are some things that affect that? Size is one. So let's talk about size. What do you think forms stronger ionic interactions? Smaller things or bigger things? Well, we'll find out.
I mean, I know cesium and francium and iridium are a lot more reactive than hydrogen and lithium.
So let's look at some different alkali metal chlorides and compare them. So what do you see there? What does that tell you? Smaller is more. Smaller makes a more stable or tighter energy compound. What do you think that is?
There's more shield. There's less shield.
Well, we're not talking about the electrons right now. We're just talking about kind of the charges coming together. Positive and negative charges. Why might smaller charges pack together more tightly than larger charges? Or more strongly than
There's less repelling of the nucleus.
Yeah, it's
like the two positive charges from the nucleus aren't repelling.
kind of, but with the actual charges, yeah. Yeah, but we want to know why. Like, what is it about smaller ions that makes them lower energy when they pack together? We can think of something called charge density. The idea that if you have, let's say, a positively charged lithium ion, that positive charge is spread over the surface of the ion. So it's like distributed over the surface. If it's sodium, it's still +1, but that +1 charge is distributed a little bit bigger. +1 distributed bigger, +1 distributed bigger. So if you look at an individual point on that shell, it has actually a lower bit of charge, if you want to think about that, the bigger the surface area is. So the charge density increases as the thing gets smaller. It also tells, that's part of it. The other part of it is just the radius. We talked about ionic or atomic radiuses. If things are smaller, then the distance between their charges is also smaller, and so therefore the attractive force is greater because they can just be closer together. So like what you were saying with the, I think you were saying that, right? That the charges are actually closer together, and that makes them stronger. So the smaller things that are comparably charged are going to have the greater lattice energies. All right, there's one other thing that affects lattice energy. What else do you think might affect it, besides size of the ions?
Number of electrons given up or taken in?
Yeah, so let's say the charge. So what do you think? Do you think that higher lattice energies occur with higher charges or lower charges? Why lower? So we're talking about the strength of the attractive force between the ions. Do you think that attractive force is greater with higher charges or lower charges? It's higher. Why? Yeah, because remember that the Coulombic force, the force between two charges, is dependent on the magnitude of the charges and the distance between them. So we already talked about the distance between them thing with the sizes. If the charges are greater, then the attractive force is also greater. So similar to this one, if we looked at two comparably sized kind of elements or compounds, sodium fluoride and calcium oxide, look at the difference in those lattice energies. Because sodium fluoride is a +1 -1 compound. Calcium oxide is +2 -2, so you have a much greater lattice energy for the +2 -2. And you can see the magnitude of that effect is much greater than the size effect. So the charges actually have a much greater effect than the radius. And you can see that even here. So in those compounds, the distance between the distances there are pretty comparable. In fact, the calcium oxide is a little bit bigger. But because of those higher charges, the lattice energy ends up being much, much stronger. All right. So to summarize, well, I guess that would be ionic radius. Increasing ionic radii lead to whoops, sorry, that should be lower. And the reason we have to use that word magnitude is that it's more negative or less negative. So if your ions are getting bigger, the lattice energy we would say is smaller, but because the sign is negative, sometimes that can get confusing. So as long as we understand that we're talking about the size of the number, the magnitude of the number, and not whether it's negative or positive, that works. If you read in the book, they say lattice energies become less exothermic, meaning less negative when the ionic radius increases. Okay. And if we say increasing charges, those would lead to higher magnitude lattice energy. Okay. And so that's really all we're going to say about ionic compounds at this time. We'll revisit them more in chapter 12 when we talk more about the structures of solids. But for now, the important thing is just to recognize how to judge lattice energies based on those two factors. Think you can do that? Okay. I know you can. All right, let's get into covalent bonding and start looking at some structures. All right, as we talked about before, covalent means that the atoms are so close that electrons can exist within both valences at the same time. And that is the definition of a covalent bond. Just to be clear on our notation here, if we look at something like a water molecule, there's a couple ways we can think about that. So we know that water is made up of 2 hydrogens and an oxygen. If we draw the valence electrons on those atoms like this, we can notice a couple things. One, the number of valence electrons, but also kind of the spaces, or where these atoms would like to have electrons. Is kind of those spots. So if those spots were filled, then those electrons would be lower, or those atoms would be lower energy. They'd be happier. They'd be more stable. So one way, which we just talked about, of doing that is making ions. So hydrogen can either lose its electron and become a +1 ion, or it can gain an electron and become -1 hydride ion. Oxygen can gain 2 electrons, become an oxide ion. That's one way of satisfying that condition. But another way of satisfying that condition is for the atoms to move so close together that their electrons are actually in both valences at the same time. So if these things were to come close enough together, we might have this kind of a situation. And the way we would do our accounting for this, in terms of counting up which electrons are on which atoms, because they're so close, all of the electrons actually count in each valence that is the shared ones. Any shared electrons count in both valences that are sharing them. So if I were looking at just this hydrogen on the left, I would say that right now in this compound, that hydrogen atom has 2 valence electrons, which is a full shell for the hydrogen. Now let's be careful there. We're not saying that hydrogen atom by itself has 2 valence electrons. We know that a free hydrogen atom has 1 valence electron. But in this compound, it now has 2 because one of those oxygen electrons is also in hydrogen's valence. They're so close together that those electrons are actually in both places, in both orbitals. In the next chapter, we'll talk about what it means for the electron to actually be in those orbitals. But for now, we'll just say that they are there. So then if we move over and look at the oxygen, same thing. We're going to include all of these electrons, the ones that oxygen brought to the party, as well as the ones that it's sharing with hydrogen, and say that in this compound, oxygen has 8 valence electrons. And then this other hydrogen, same idea, that one would have 2 valence. So that's what we call a Lewis dot structure of water. We draw these dots, we combine them, put them together. Normally, we won't use that type of a structure too much because one thing that it obscures a little bit is which things are connected to what. So in other words, which electrons came from the oxygen originally and which ones are being shared with the hydrogen. It also makes it hard to represent shapes because they have to kind of all just be squished together like that. So we often, instead of using those dots, we use a line. But we mean the same thing. So you're probably more used to seeing something like this. Okay. And that's what we would call a Lewis structure. But importantly, that line has a very specific meaning. It means two shared electrons. It doesn't just mean things are kind of connected or that they're by each other. It means now for us specifically that those two electrons are shared. They are covalent. They're in both valences at the same time. The dots on the oxygen are extra electrons that we might refer to as, give myself a little more room here. Non-bonding, not non-boning. Which are sometimes also referred to as lone pairs, meaning pairs of electrons that are not involved in covalent bonding. If you go on and take some organic chemistry, these kinds of ideas will become very, very important. The ideas of how the lone pairs become bonds or how they kind of reach out to help make connections to other atoms, all the accounting of which electrons are where becomes very important. Okay, so we talked about the sharing of electrons, but in many compounds that sharing is not equal. And it gives rise to something called bond polarity. So if we look at a bond between two of the same element, like two hydrogen atoms, remember that represents those two shared electrons. So each hydrogen atom brought one electron, and now they have two shared. So we would say each of those hydrogens has two electrons now in its valence shell in the compound. And would you say those electrons are shared evenly between the two, or they're more lopsided on one side or the other? Evenly. Why? Yeah, it's the same thing on both sides. There's no reason that they would be more on one side. Now, at any instantaneous moment, they could be, because remember, we don't know where the electrons are, or if we do know where they are, then we don't know how fast they're going. So they could be there at any given moment, but on average, they're going to be shared evenly between the two atoms. So this is, maybe we can represent this kind of like this. We'll just say that's the electron distribution. And it's basically even around there. Okay. So if we compared that to a similar molecule, HF, so HF has some lone pairs around the F, but it still is just a single bond between the H and the F, much like the HH. But in HF, we have a very uneven electron distribution. In HF, the electrons are pulled more toward the fluorine side and away from the hydrogen side. And that leaves a separation of charge. So this side kind of becomes more positive because the electrons are pulled away from it. And this side becomes more negative because the electrons are pulled toward it. And electrons are negatively charged. If something has a positive side and a negative side, then we call it polar. So we would say that this molecule is polar. And another way that's sometimes expressed is that it has a dipole. Dipole means just two, like it's separated into two poles. So we would say this is a polar molecule or it has a dipole because of that separation. the way we express this when we're not drawing that kind of a picture is to say that there's partial positive on one side and partial negative on the other side, and we use a Greek letter delta for that. So this one is delta positive, and this one is delta negative, which means a little bit negative, a little bit positive. Those are partial charges, because if they were full charges, it would be an ionic compound. But we're saying this is still covalent. It's just not evenly shared. And so that would be called a polar covalent compound. Yes?
So then anything that's polar also has a dipole?
Right. Yeah. We're gonna be a little bit more subtle than that, like in the next chapter, because you can have a polar bond, or you can have an overall polar molecule. But same idea. The dipole is like the mathematical quantity. Like a dipole is a specific vector that has like a specific magnitude that tells you there's this much negative and this much positive. So that's like the quantity. And polar is more like a descriptive term, like this is polar. So if you want to be really precise, you might say like a non-zero dipole or something means that something is polar, because the dipole is like the quantity. So one way that we have of measuring this is called electronegativity. Electronegativity is the ability of an atom to attract electrons in a covalent bond. And it's a measurement. It's an experimental measurement. You look at comparable compounds, you measure their polarity by various methods, and then you come up with a number that tells you the electronegativity. So there isn't really a super convenient chart here, but there's a pretty one, so we'll just kind of leave it over here and refer to it as we need to. But this kind of gives you a visual representation of this electronegativity. So it's this number that's a result of experiment. It's not calculated by like looking at orbitals or whatever. It's calculated from experiment. But each element is given a particular value, and we can kind of see on the periodic table where are the areas of very high electronegativity. The top right, does everybody see that? Those are kind of the highest ones. And where is the very low electronegativity? Bottom left, yeah, way down here. So you have a pretty nice trend to remember. You don't have to remember the individual numbers for electronegativity, but you can often solve problems of like, is this polar or not, by looking in general at the trend. So if you have something that is very far to the right, like fluorine, which is the most electronegative element, bound to something like carbon, which is a few spots away, then you have a pretty big difference in electronegativity, and that difference in electronegativity is what gives rise to the polarity. So when you have two atoms bound that have a big difference in electronegativity, that bond becomes polar. Let's quantify that a little bit more. So let's draw our periodic table here. So the general trend is for electronegativity to increase up and to the right to fluorine, which is the most electronegative. Electronegativity increases toward fluorine.
Well, on the other picture, just cut off the noble gases. So
Right.
Should we include the noble gases on the periodic table?
Noble gases don't really make a lot of compounds. There are some compounds known of the noble gases. You can assume that they have extremely low electronegativities. I think they have not actually been measured, and that's why we don't have that information. You might be able to look it up somewhere. All right, so what ends up happening then is we have this kind of continuum where you have this perfectly nonpolar thing like HH, where the electrons are distributed perfectly and there's no plus or minus on either side. Then the other extreme is you have an ionic compound, where you have a perfectly minus ion and a perfectly positive ion. But in reality, most things are kind of in the middle there, and kind of on a one scale for another. So we have to kind of set up some boundaries so that this makes sense. And the boundaries that we set up here kind of look like this. We're going to call a polar covalent bond anything where the difference in the two electronegativities is higher than 0.4 but below 2. Below a difference of a difference of 0.4 or less, we're going to call that nonpolar. We're going to say those electrons are shared equally, and that is a nonpolar bond. And above 2, we're going to call that ionic. We're going to say there's so much separation of charge. That's essentially always going to be a metal and a nonmetal. There's so much separation of charge that we have an ionic situation. And that's really going to be thought of more as an ion, more as ions. So, a little bit more nicely. All right, so we can see that. And of course, that's just a guideline for thinking about things. We can actually measure how good of a guideline that is by something like this. So what you see here is there's that electronegativity difference on the bottom, on the x-axis. So here's our very nonpolar things. Here's our very polar things. Remember that cutoff point for ionic we said was 2. But what it's graphed against is the ionic character, which is an actual experimental measure of how ionic something is based on that, like what would the dipole moment be if the electron were completely transferred. So you can see that in some cases it matches up pretty nicely. If electronegativity difference was exactly correlable, I don't know if that's a word, correlatable, to percent ionic character, you would expect a nice straight line. Since we don't have that, what that's telling us is some compounds are more ionic than their electronegativity difference predicts, and some are less. So if we look at, for instance, a compound like HF, has a pretty big electronegativity difference, but actually has very little ionic character. Whereas something like CSI, cesium iodide, has about the same electronegativity difference, or even a little less, but really is quite ionic, much more ionic. So it's not an absolute predictor, that electronegativity difference, but it's a pretty good guideline. It does start to break down when we start looking at metals, because the metal and nonmetal compounds are going to be definitely ionic, but sometimes the electronegativity difference isn't quite that big. Okay. Everybody okay? Maybe. All right, we're going to do one more thing. We only got about 10-15 minutes left. And that is drawing Lewis structures. Have you guys drawn Lewis structures before? Previous chemistry classes? Some people yes, some people no. Okay. So what happens when you have larger molecules? All we've talked about so far is you have 2 atoms, you connect them with a with a line, and they share electrons, and they become a structure. But what happens if you have larger atoms than that? Then we have to write a Lewis structure, and the idea of kind of like piecing it together, so taking the Lewis dot structures and just like kind of fitting them like we did with water, that doesn't always work. It's not the best way to do it. So let's come up with a systematic way of doing this. And if you've done it in the past and you have a method that works, stick with that method, but I'm going to show you how I do it. All right, so let's say we want to draw a structure of CO2, carbon dioxide. We want to know how those atoms connect to each other. So first what we want to do is count up the total number of valence electrons, because all the bonds and all the lone pairs have to account for all the valence electrons in that compound. So the total valence electrons is going to be the sum of the valence electrons of each of the atoms. So carbon, we look at the periodic table, it's in column 4. So carbon has 4 valence electrons. Oxygen, we've talked about a lot today, has 6 valence electrons, and there's 2 of them. So we're going to add those all together. So we would say this compound has 16 valence electrons to work with. And we sort of put them in a big pot. So rather than saying carbon has these 4 and oxygen has these 6, we say here's the total that we're going to work with, and we put them all together. So that's the first step. Count up your valence electrons. Second step, draw a basic shell of how this thing might be connected. And when I say might, we could be wrong at this point. There's various ways we could connect this. Well, okay, there's 2 ways we could connect this, right? We could connect it COO, or we could connect it OCO, or we could do something even weirder, like put in a triangle or something like that. But we'll stick with those possibilities for now. So one of these is right, one of these is wrong. How do we know which one is which? Any idea?
See if all of, I think the right way to word this. Make sure that all of the, back to
Julia, you want to jump in?
I thought that the one on the top would be wrong, because if you have carbon that has right 4 valence electrons,
Uh-huh.
the 2 on each side, wouldn't you just fill it out from there?
Yep, yeah, that's right. Anybody else? So the real answer is you don't necessarily know. By the time we fill in all the electrons and talk about a couple other things like formal charge, we will be able to tell which one's right and which one's wrong. But just looking at it like this, from a CO2 to know which one it's connected to, there isn't a way right now to know absolutely this one is right and this one is wrong. We can have a couple clues. So this one is right, as you probably know if you've seen the structure of carbon dioxide before. We'll talk about why that is in a bit, but how you can guess that it's right is usually the central atom is first in the formula. That's not always true, but often it is. So it's a good first guess. Also, the right one often ends up being the most symmetric. Again, not every time, and we'll know by the end if it works or not. But a good first guess is to kind of take those rules and start with those. Okay, so we'll start with that. And then our next step is to fill in the rest of the valence electrons so that we count up to 15, but we can't forget we already have 4 accounted for. We have to count those 2. So there's 2 electrons in this bond. There's 2 electrons in this bond. So that means we've got 12 left, right? Everybody see that? 2, 2, taken away from 16 means 12 left. So what you do is you start putting those 12 electrons around the atoms until they get to 8 because of the octet rule. So we would go, all right, so this one needs 6 more electrons to get to 8 because it counts both of the electrons from the covalent bond, and then it needs 6 more, and that's 8. Then we could do the same thing with the other oxygen. Okay, now that one's got an octet, but now we got a problem. What's our problem? We're out of electrons, and that middle carbon atom doesn't have enough electrons. It hasn't gotten to 8 yet. So what do? Yeah, we need to turn some of those electrons into shared electrons, which means a bond. So if instead of taking one of these pairs of electrons, instead of putting it directly on the oxygen, come on, eraser, what are you doing? Okay, it doesn't want to erase things. Oh, there we go. So instead of taking one of those and putting it just on the oxygen, we could have made that one a shared pair of electrons, which would put it right here. And now it counts for both the oxygen and the carbon. And then we can see if we do that one more time, now we have something that works. So let's check it again. The oxygen on the left, we would count 2, 2, 2, 2. That's 8 electrons, so it's good. The oxygen on the right, 2, 2, 2, 2, 8 electrons, it's good. The carbon in the middle, 2, 2, 2, 2, 8 electrons, it's good. And then final check, count up all the electrons and make sure it's the same number as your original count of the valence electrons. 2, 4, 6, 8, 10, 12, 14, 16. If you've met both those categories, or both those criteria, you've probably got the right Lewis structure. There's going to be a couple more rules later on, but for now, you probably got the right Lewis structure. All right, think you can do that? Okay, you try one. See if you can make a Lewis structure for nitrate ion. So the tricky thing here, that I'll get you started with, is when you do your electron count, it's a negative charge, which means you have to add an extra electron. So a positive charged ion, you would take away electrons. Negative, you'd add. So we can do that part together, and then you can work on the structure. So it would be 5 valence electrons from nitrogen, plus 6 for oxygen, and there's 3 of them. And then we add 1 more for that negative charge. So that ends up being 24 total valence electrons. See if you can draw a structure from there. Go with the structure? Anybody want to draw it? Yeah? Thanks. Do you want to draw it on the computer or on the board?
I'd rather do board.
Okay.
Because I don't know how.
Yeah, it kind of sucks.
This thing.
You can just use that marker.
Because I'm used to Sketchpad. There it is. Alrighty.
All right, thank you. So what do you think? That's good? All right, anybody have any issues with it? So when you're evaluating the Lewis structure at this point, there are really two things you're looking for. Go ahead. Nicola.
I just have a question. So I didn't like draw, like I just did them all diagonal.
Yeah.
Does it have to be like one has to be straight across from it and then the two?
Well, isn't it all diagonal depending on how you rotate it?
Oh, okay, I got it.
Yeah. No, at this point we haven't talked about molecular geometry, so there isn't a specific geometry you have to draw it.
Okay.
If you did it straight across and down, or like straight and up, or whatever, that's fine too.
Okay.
What we're looking for now is, does every element have an octet of electrons, so 8 electrons around the atom, and is the total number of electrons correct? So in this one we would say 2, 4, 6, 8, that oxygen's good. 2, 4, 6, 8, nitrogen's good. 2, 4, 6, 8, oxygen's good. 2, 4, 6, 8, oxygen's good. So each of those have an octet. That's great. Then total number 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So we got the right number. So that fits the criteria. So it's a good structure. All right. So just like anything else we've done, this takes practice. So make sure that you are practicing. I'll draw this on the notes here too, so we have it. On Wednesday, we will have a quiz. The Lewis structures will not be on the quiz, but Chapter 8 will be on the quiz. So orbitals, electron configurations, some of the stuff from the exam, but then also the trends that we talked about today will be on the quiz. Then on Wednesday, we're going to talk about more Lewis structures, more complicated ones with expanded octets or less than an octet, and how to evaluate structures that are technically correct, but some might be better than others. So lab tomorrow is the flame test lab, right? Yeah, that's a fun one. People like it because you get to set stuff on fire, but you please do not set off the fire alarm, especially because in the labs, if the fire gets up to the sprinklers, then they turn on and we all get wet. So it'd be good if we did not do that. So there's no pre-lab for tomorrow. I will hopefully have your exams. Somebody said the withdrawal deadline is tomorrow. It is not. It is next week, July 1st. July 1st is the drop deadline. But I will hopefully have your exams back for you in lab tomorrow. And the flame test lab is pretty fun and pretty easy. I think you'll like it.
Are we going to go over the exams in that?
We will probably not. We'll go over the exams on Wednesday, so you can just bring them back on Wednesday to go over it. All right. Other questions? Sorry, we had to take a break outside. I will put it on as soon as I finish it. It may not be until tomorrow morning, until before class. Sometimes I can't get stuff done online at home very well, so.
If you can do what you did last time, just give us the exams when we're done the quiz.
On Wednesday? I could, but I feel like if they're done by tomorrow, people are going to want them tomorrow. If you want to wait, I'll hold yours and give it back to you at the quiz if you want.